Welcome to the Deep Dive. Today, we're delving into something pretty profound, actually. We're looking at the geological timeline, at one of the rarest transformations Earth has ever seen. We are living through, right now, a mass extinction event, the Sixth Extinction.
That's right.
But here's the really critical part, the thing that sets it apart. Unlike the previous 5 big ones, asteroid impacts, massive volcanoes, that sort of thing, this one, it's driven entirely by one species.
Yeah. Us, Homo sapiens.
Us, exactly.
And that's our goal in this deep dive, isn't it? To unpack how we got here. We need to understand not just what's happening now, the mechanisms, but also how we even came up with the idea that a whole species could just disappear.
Right, because that wasn't always obvious.
Not at all. So we'll be connecting things like 18th century fossil finds with modern ocean chemistry. We're linking the fate of frogs in Panama to, well, the massive impact of human global trade. It's all connected.
And before we even get into the history of the idea, we really need to grasp the sheer speed of what's happening now. The scale of loss is, well, it's terrifying.
It is.
The research shows that for amphibians, for example, extinction rates are calculated to be potentially 45,000 times higher than what you'd normally expect. The background rate?
45,000.
45,000 times. I mean, that number, it just fundamentally changes how you have to think about life on Earth, doesn't it? The whole texture of the biological world is being kind of shredded as we speak.
Yeah. And if you're looking for like a starting gun for this modern crisis, the amphibians are probably the clearest, most immediate warning sign.
That story of the golden frog in Panama,
Mm-hmm.
it's just heartbreaking. I tell up as a techie.
It really is. El Valle de Anton, this town inside an old volcanic crater.
Yeah.
There used to be a stream there they called Thousand Frog Stream. Just tells you how common these beautiful golden frogs were.
Wow. Thousand Frog Stream.
And now, the stream's quiet. If you go to the market, you can buy little ceramic golden frogs as souvenirs. Because the real ones, they're basically gone from the wild there.
That's devastating. And the scientists, the herpetologists who study them, they saw this happening.
Oh, absolutely. In real time. One researcher, I think from Zoo Atlanta, mentioned how his career now feels more like paleontology, like he's studying things that are already gone, at least from their natural homes.
Studying ghosts.
Pretty much. And the weird thing was, it wasn't just in populated areas. These frogs were vanishing from really pristine, remote places, too. High up in the Sierra Nevada, deep in Central American forests, places you'd think were safe.
So that must have been the big mystery at first, right? If they're dying off in disturbed areas and perfect habitats, what on earth could be causing it?
Exactly. It felt like some kind of coordinated global attack, which in a way it turned out to be. The culprit they eventually identified is this fungus, Batrachocutrium dendrobatidis.
We call it breed for short, right?
Yeah, beeted. It's a type of fungus, loves the cold, lives in water, and its spores can move around. But here's the catch. Beet itself can't cross oceans. It can't climb over mountain ranges on its own. So how did it end up causing a global pandemic among frogs?
Okay, so this is where we come in. Human movement.
Precisely. Global trade. Beet seems to be native to some parts of the world, maybe Africa, where local frogs evolved with it. But it's a novel pathogen, a new disease in places like the Americas and Australia. Their frogs had no defense.
So we accidentally shipped it around the world.
That's the overwhelming consensus. It hitched a ride. We basically acted as a transport network, breaking down barriers that had kept ecosystems separate for millions of years. It's this unprecedented biological reshuffling.
How did it travel? What kind of trade are we talking about?
Well, there are a couple of main theories. One points to the African clawed frog.
Oh, I've heard about this. They used them for pregnancy tests.
Exactly. Decades ago, before modern tests, you'd inject a woman's urine into one of these frogs, and if she was pregnant, the frog would lay eggs. So these frogs were shipped absolutely everywhere.
Wow.
And they can carry abroad without getting sick themselves. Perfect silent carriers.
Okay, that makes sense. And the other theory?
The North American bullfrog. They're farmed and exported on a huge scale, especially for food frog legs.
Right.
And again, they're pretty resistant to broad but can carry it. So whether it was frogs for medicine or frogs for dinner, they got loaded onto ships, onto planes, moved across continents in a way that just never could have happened naturally.
So it wasn't just like pollution in one spot. It was us physically moving life forms around, creating this global biological mixer.
A global mixer is a great way to put it. And the thing is, amphibians are hit hardest, maybe, but this isn't just about frogs. The scale of the crisis is enormous.
Yeah, the numbers are pretty grim across the board.
They are. You look at the data. Something like a third of all reef-building corals are threatened, a third of freshwater mollusks, a quarter of all mammals, a fifth of reptiles, a sixth of birds. They're all described as headed toward oblivion.
And when you dig into the reasons for each one, maybe it's habitat loss here, poaching there, a new disease somewhere else.
You trace it back, and researchers find they are, quote, inevitably led to the same culprit.
Us. Our sheer numbers, our movement, our resource use. It all comes back to that.
It's the unifying force behind all these seemingly separate crises.
It's quite a realization that we are the single driver. But let's take a step back. The actual idea that a species could just disappear forever, that concept itself is relatively new, isn't it?
Oh, yeah, it's fascinating. For most of human history, the idea just wasn't there. Think about the ancient Greeks, like Aristotle, or the Romans, like Pliny. They wrote encyclopedias of animals, but they didn't distinguish between living ones and ones that might be lost.
They assumed the world was complete. Like everything that ever existed must still be out there somewhere.
Exactly, a kind of perfect, unchanging creation. And this lasted for centuries. Even Carl Linnaeus, the father of modern taxonomy, in his big 1758 Systema Naturae, only listed species he believed were currently alive.
I read that even Thomas Jefferson hoped Lewis and Clark would find living mastodons out west. He just couldn't accept that nature would let a whole race of animals die out.
He really couldn't. It took the French Revolution and a brilliant naturalist named Georges Cuvier, Jean-Léopold Nicolas Frédéric Cuvier, technically to shatter that view.
And the key was these weird bones being found in America. The mastodon.
Yes, Mammoth americanum. Bones started turning up in the Ohio River Valley in the 1730s. Huge femurs, tusks, looked like an elephant mostly.
But the teeth were different.
Very different. Really bumpy molars, not like elephant teeth at all. So they called them things like tooth of a giant, or later the American incognitum, the unknown American thing.
The mystery animal.
Right. Cuvier was working at the Natural History Museum in Paris, studying these bones and comparing them meticulously with skeletons of living elephants, Asian and African. His radical conclusion, based on this detailed anatomy, was that this incognitum wasn't hiding somewhere. It was gone. A lost species. Vanished from the earth.
That must have been a huge conceptual leap. How did he follow that up?
He quickly identified other lost species from fossils, the woolly mammoth, the cave bear. He basically invented the concept of extinction, arguing that Earth's history wasn't smooth, that there had been a previous world destroyed by catastrophes.
So he proposed these sudden violent events, revolutions on the surface of the earth, he called them.
That was his term, yeah. Catastrophism, the idea that Earth's history was marked by these sudden dramatic upheavals that wiped out life.
But that idea didn't exactly sit well with the emerging scientific thinking of the time, did it? Like Lyell and Darwin.
No, it flew right in the face of uniformitarianism, which was championed by Charles Lyell and later embraced by Darwin. Their view was all about slow, gradual, constant change. Geological forces acting bit by bit over vast eons. They really disliked the idea of sudden, almost biblical-seeming catastrophes.
So how do they explain extinction if it wasn't catastrophes?
For them, extinction was a much slower, quieter process, more like individual species just fading away, outcompeted in the struggle for existence as newer, better adapted forms emerged. Darwin wrote about species being swept away. It was seen as a consequence of gradual evolution, not sudden violence.
And those abrupt disappearances in the fossil record, like the ammonites, how do they explain those?
They basically argued the fossil record was incomplete. Like missing pages in a book, they'd say, oh, we just haven't found the fossils showing the gradual decline. They didn't see the gaps as evidence of sudden events. The slow and steady view fit much better with their theories of evolution.
Okay, but let's go back to the mastodon that started it all for Cuvier. He thought it vanished maybe 5,000 or 6,000 years ago in one of his catastrophes.
That was his estimate based on what he knew then. But we now know, thanks to modern dating, that the American mastodon disappeared around 13,000 years ago.
And what else happened around 13,000 years ago?
It's precisely when modern humans arrived and spread rapidly across North America. It lines up almost perfectly with the extinction of not just mastodons, but mammoths, giant sloths, saber-toothed cats, the whole American megafauna.
Whoa. So Cuvier was right about the suddenness. He saw catastrophe in the bones, but he just got the cause wrong.
In a really uncanny way, yes. He correctly identified a rapid revolution. He just didn't realize the revolution was. Well, it was us arriving on the scene. The megafauna extinction wasn't caused by floods or earthquakes. It looks very much like it was caused by human hunting and landscape changes. The catastrophe Cuvier detected was, in fact, Homo sapiens.
Okay, so Cuvier sensed a catastrophe with the mastodon. But the gradualist view, the slow extinction idea from Lyell and Darwin, really took hold for a long time.
Over a century, right?
It dominated geological and biological thinking, absolutely. The idea of a sudden global wipeout seemed almost unscientific.
Until the KT boundary, the end of the dinosaurs.
Exactly. And the story there starts in Italy, in a gorge near Gubbio, with a geologist named Walter Alvarez in the 1970s.
Right, who's looking at this weird thin layer of clay.
Yeah, maybe half an inch thick,
Yeah.
sandwiched right between the rocks, full of late Cretaceous fossils, the last dinosaurs, and the tertiary rocks above it, which had very different post-dinosaur life forms. This clay marked the boundary, the KT boundary, now often called the KPG boundary.
And he wanted to know how long it took for that clay layer to form.
That was the question. And his father, Luis Alvarez, who was a Nobel Prize-winning physicist, had this really clever idea.
The iridium. The iridium. Luis knew iridium is super rare on Earth's surface because most of it sank to the core when the planet formed. But it's much more common in meteorites and cosmic dust that constantly drifts down from space.
Okay.
So the thinking was, if this clay layer formed slowly, over thousands of years, it should contain a certain measurable amount of iridium from that slow accumulation of space dust. If it formed quickly, well, something else must have delivered the iridium.
And when they tested it?
The results were absolutely stunning, off the charts. Not just in Italy, but later in samples from Denmark, New Zealand, all around the world, right at that boundary layer. The amount of iridium was orders of magnitude higher than you'd expect from normal cosmic dust. Meaning, the iridium must have arrived all at once in a massive dose from an extraterrestrial source.
No.
The inescapable conclusion, a giant asteroid or comet hit the Earth, kicked up enormous amounts of debris laced with iridium, and that debris formed the clay layer as it settled globally. And that impact caused the mass extinction.
Wow. But I remember reading the scientific establishment didn't exactly roll out the welcome mat for this idea.
Oh, not at all. There was fierce resistance, especially from paleontologists deeply invested in the gradualist model. They hated it.
Why? It sounds like compelling evidence.
Because it felt like a return to Cuvier's catastrophism, which they'd spent a century dismissing. It implied that random, violent luck could just trump millions of years of evolutionary fine-tuning. They called the Alvarez theory codswallop, said it was an artifact of statistics, claimed the physicists didn't understand biology. The New York Times even ran an editorial mocking the idea of looking to the stars for earthly events.
That's incredible resistance. So what finally convinced people? What was the smoking gun beyond the iridium?
It was the accumulation of more evidence. First came shocked quartz. These are quartz crystals with microscopic deformations caused by incredibly intense, sudden pressure, the kind you only find at nuclear test sites or...
Meteor impact traders.
Exactly. And they started finding shocked quartz grains worldwide, specifically within that KT clay layer. Then came evidence of colossal tsunamis around the Gulf of Mexico from the same time period.
And finally, the crater itself.
The crater itself, the Chicxulub crater, 100 miles wide, buried under the Yucatan Peninsula. It had actually been detected years earlier by oil company surveys, but they thought it was a volcano and forgot about it.
Seriously?
Seriously. But once the Alvarez theory pointed researchers in the right direction, they drilled cores and found melted rock, glass spheres, direct evidence of a massive impact, dated precisely to 66 million years ago. That basically sealed the deal. Catastrophes do happen, and they can reshape the entire biosphere.
Which brings us to the poor ammonites. These creatures were incredibly successful for hundreds of millions of years, right? Like shelled squids.
Yeah, ammonites were amazing, related to modern nautiluses and squid, with those beautiful spiral shells. They thrived in the oceans for over 300 million years, diversifying into countless forms. Neil Lanneman, a paleontologist, studied them closely, especially fossils from New Jersey right up to that KT boundary.
And what did he find? Were they already declining like the gradualists thought?
No, that's the key. Landman's work showed many ammonite species were doing just fine, abundant and diverse right up until the moment of impact. They didn't fade away, they were abruptly wiped out.
So why did the impact hit them so hard?
100% extinction for them, right?
Total extinction for the ammonites. The impact's immediate effect was this global cloud of dust and aerosols. It blocked sunlight, probably for months, maybe years.
Yeah.
Photosynthesis collapsed on land and in the sea. Temperatures plummeted. It was a global winter.
Okay. And on land, that wiped out anything bigger than, what, a cat, including the non-avian dinosaurs.
Right. In the oceans, the ammonites had a particular vulnerability linked to their life cycle.
What was that? Their babies, the hatchlings, were tiny and planktonic. They fluted freely in the surface water, drifting with the currents. Normally, that's a great strategy for dispersal.
But not when the entire ocean surface suddenly becomes cold, dark, and maybe acidic from the impact fallout.
Exactly. Their young were completely exposed, with no refuge. They likely starved or couldn't form their shells properly. Contrast that with their relatives, the nautiluses.
They survived, didn't they? They're still around.
They are, and a key difference seems to be that nautiluses lay larger eggs, often in deeper water, and their young develop protected within that egg. They skip that vulnerable planktonic surface stage.
So it wasn't about being better adapted in a Darwinian sense over millions of years. It was just bad luck on the day.
That's what it looks like. In times of really extreme sudden stress, the evolutionary playbook kind of goes out the window. Traits that were successful for eons can suddenly become a death sentence. Fitness, in the traditional sense, loses its meaning. It was just incredibly bad luck for the ammonites.
Okay, so the KT impact was this sudden, violent event from space, pure chance, catastrophic physics. But now we shift to our current era, the Anthropocene, the age defined by human impact. How is the catastrophe we're causing different?
It's fundamentally different in its nature. It's not a single asteroid strike. It's thus. It's a constant, pervasive, global alteration of the planet's fundamental systems, its chemistry, its energy balance, driven by human activity. We've become a kind of slow-motion, grinding catastrophe.
And a huge part of that is carbon dioxide, right?
Right.
Changing the atmosphere.
Absolutely central. Burning fossil fuels, clearing forests. We've increased the CO2 concentration in the atmosphere by about 40% just in the last 2 centuries. Maybe more now.
And a lot of that CO2 doesn't just stay in the air.
No, the oceans are like a giant sponge. They absorb roughly a third of the CO2 we emit.
Which leads to ocean acidification. That sounds bad.
It is bad. When CO2 dissolves in seawater, it forms carbonic acid. This lowers the water's pH, making it more acidic. The average pH of the ocean surface has already dropped from about 8.2 to 8.1 since the Industrial Revolution.
Now, 0.1 sounds tiny, but the pH scale is logarithmic, like the Richter scale, right?
Yeah.
So that's actually a big deal.
It's a huge deal. That 0.1 drop represents about a 30% increase in acidity. 30% in just 200 years. And if we keep going with business as usual emissions, projections suggest the pH could fall to around 7.8 by 2100.
Which would be
About 150% more acidic than pre-industrial levels. The ocean chemistry is changing at a rate potentially faster than anything seen in tens of millions of years.
That's staggering. The source material mentioned that every American every day effectively pumps 7 pounds of carbon into the sea, just altering its basic chemistry. What does a more acidic ocean actually look like?
Well, scientists can get a preview by studying places like the volcanic vents off the coast of Ischia in Italy, Castello Aragonese.
Natural CO2 vents.
Exactly. They bubble CO2 directly into the water, creating localized zones of higher acidity, mimicking what future oceans might be like. It's like a natural laboratory, an underwater time machine.
And what do they see there, near the vents?
It's pretty stark. As you get closer to the vents, into the more acidic water, certain species just disappear. Barnacles, for example, are gone. And organisms that build shells or skeletons out of calcium carbonate, they're called calcifiers, they really struggle.
Things like corals, clams, sea urchins.
Yes, limpets too. They found one local limpet species, Patella caerulea, whose shells in the high CO2 zones were thin, pitted, almost transparent, wasted away.
Because the water is literally making it harder for them to build their shells.
It increases the energetic cost. The basic building blocks, carbonate ions, become scarcer in more acidic water. So these animals have to spend much more energy just to precipitate their shells, energy they could otherwise use for growing or reproducing. It's like trying to build a house while someone keeps stealing your bricks.
And this double whammy, the changing chemistry from acidification and rising temperatures from climate change, is hitting coral reefs especially hard, isn't it?
Devastatingly hard. Coral reefs are just incredibly important ecosystems. These massive structures built by tiny animals, these polyps, they're like the rainforests of the sea.
Supporting huge amounts of biodiversity in otherwise nutrient-poor tropical waters. Darwin called it a paradox.
A paradox, exactly.
Yeah.
And they face both threats. Acidification makes it harder for the corals to build their limestone skeletons, their foundation, and warming causes coral bleaching.
Explain bleaching again. That's when they turn white.
Yeah. Corals have this vital symbiotic relationship with tiny algae called zooxanthellae living inside their tissues. These algae photosynthesize, providing the coral with food and giving it its color. But when the water gets too warm, the corals get stressed and expel these algae.
Leaving them bone white.
Bone white. And if the heat stress lasts too long, the corals starve and die, leaving just the white skeleton, which eventually crumbles.
The outlook sounds incredibly bleak for reefs.
It's terrifying. Some scientists project reefs could be the first major ecosystem to become ecologically extinct in the modern era. One study of the Great Barrier Reef predicted that by 2050, much of it could be just rapidly eroding rubble banks. Already, about a third of reef-building coral species are considered threatened with extinction.
Wow. Okay, so that's the ocean. What about warming on land? How are things like forests responding?
Similar problems, especially with the rate of change. There's work by Miles Silman, an ecologist who studied forest plots at different elevations in the Andes in Peru and Manu National Park.
Trying to see if the trees are moving uphill as it gets warmer.
Exactly. And the key finding is that today's warming is happening maybe 10 times faster or even more than the natural warming that occurred at the end of the last ice age.
10 times faster. So species have to migrate or adapt 10 times quicker just to keep up?
Right. And Silman found that some trees, the more adaptable or faster dispersing ones, like certain species in the Schefflera genus, are managing to shift upslope, chasing the cooler temperatures. They're the fleet-footed, so to speak.
But not all of them.
No. Many other species, particularly slower growing or less mobile ones like some ilex species, are basically just sitting there. They can't move fast enough. Their suitable climate zone is shifting away from them faster than they can migrate.
And when trees do move upslope, they often run out of mountain height. The available area gets smaller.
Precisely. Which brings us to a fundamental ecological principle, the species-area relationship.
Explain that. How does losing area lead to losing species?
It's a well-established pattern. The larger the area of habitat, the more species it can support. But it's not linear. If you shrink a habitat, say by 90%, you don't just lose 10% of the species. You lose far more, maybe 50% or even higher over time.
Why so much?
Because the remaining smaller areas support smaller populations, which are more vulnerable to random events. It's less resilient, harder for species to recolonize if they blink out locally. Connections are broken.
And when scientists apply this species-area relationship to the potential habitat shifts caused by climate change,
the modeling suggests that, under plausible warming scenarios, something like 24% of all species on Earth could be effectively committed to extinction. Climate change isn't just a local threat like a bulldozer, it's reshaping the entire map of where species can live, acting like one of Cuvier's revolutions on the surface of the Earth. So we've got the changing chemistry, the rising heat, but the Anthropocene extinction is also being driven by how we're physically rearranging the landscape. Two big factors here are habitat fragmentation and invasive species.
okay, let's start with fragmentation. Chopping habitats up into little pieces. The classic study is that Amazon project, right? The BDFFP.
Yes, the Biological Dynamics of Forest Fragments project, an incredible long-term experiment. They deliberately created forest islands, patches of rainforest, like one called Reserve 1202, surrounded by cleared land, by cattle pasture, mimicking what happens everywhere with development.
Islands on dry land. And what did they find happens inside those fragments over time? What is fragmentology?
Well, first, they often saw an initial spike in density, a refugee effect, as birds and animals fled the surrounding cleared areas and crowded into the remaining forest patch.
Okay, a temporary boost.
But then, over the longer term, the consistent pattern was a degradation in the diversity. Species started to disappear from the fragments. They just bled species over time.
Why does being small and isolated cause that loss?
Several reasons. Small populations are just much more vulnerable to chance events. A bad storm, a disease outbreak, a few years of poor breeding success things. A large captive population can wipe out a small isolated one.
And there's no rescue possible.
Exactly. If a species disappears from an isolated fragment, there's no way for individuals from elsewhere to arrive and reestablish the population. The connection is cut.
The sources mention that specialist species are particularly hard hit. Can you give an example?
A great example is the obligate ant-following birds in the Amazon. These are bird species whose entire foraging strategy depends on following massive swarms of army ants, like Eciton burchellii.
The ants stir up insects, and the birds grab them.
Precisely. In a large, intact forest, there are always ant swarms active somewhere. But in a small fragment, the ant populations themselves might become unstable or disappear. And the birds that depend only on them, they can't adapt, they vanish too because their highly specialized niche collapses.
Right. Now, E.O. Wilson famously used that species-area relationship to estimate that deforestation alone should be causing thousands of species extinctions per year. But we don't always see them vanish that quickly. There's a delay.
Yes, and that delay is captured by the concept of the extinction debt.
Extinction debt. Like, we've signed the death warrant, but the execution is delayed.
That's a good analogy. Habitat loss today might doom a species, making its long-term survival impossible. But the last remaining individuals might hang on for years, even decades. So we've incurred a debt future extinctions caused by past actions that hasn't been fully paid yet. It makes the current crisis seem slower than it actually is.
Okay, so fragmentation isolates populations. What about the opposite effect? Bringing species together that should be separate, the new Pangaea.
Right, the new Pangaea. Pangaea was the ancient supercontinent when all land masses were joined. Today, through global travel and trade, we're artificially recreating a kind of biological Pangaea, mixing up the world's species at an incredible rate.
Eliminating the natural geographic barriers, oceans, mountains that kept evolution running on separate tracks for millions of years.
Exactly. Think about ballast water in ships. Huge tanks of water are taken on in one port to stabilize the ship, and then dumped out in another port on the other side of the world.
Containing
Containing potentially thousands of different species, plankton, larvae, small invertebrates. The estimate is something like 10,000 species are being moved around daily just in ballast water. Never mind plants, insects, soil microbes moving with agriculture or horticulture.
So ironically, this mixing can actually increase the number of species found in a local area, right? Like non-native plants outnumbering native ones somewhere like Hawaii.
Yes, local diversity can technically go up, but it comes at a huge cost. The loss of unique endemic species, the ones found nowhere else that often can't compete with the new arrivals. Global homogenization reduces overall global biodiversity.
And sometimes these new arrivals are pathogens, like the story of white nose syndrome in bats.
A truly devastating recent example, this fungal disease started showing up in bats hibernating in caves near Albany, New York, around 2006.
Affecting the little brown bat, which used to be super common.
Myotis lucifugus, yeah. One of the most abundant mammals in North America. White nose has killed millions of them and several other bat species too. It's catastrophic.
And the cause is a fungus that wasn't native.
That's the key. The fungus, Pseudogymnoascus destructans, seems to have been accidentally brought over from Europe, probably by cavers or tourists carrying spores on their gear.
European bats are okay with it.
Largely, yes. They co-evolved with the fungus, so they have some resistance. But for North American bats, it was a completely novel pathogen. They had no evolutionary defense.
How does it actually kill them? It grows on their noses.
It grows on their noses, wings, and ears while they're hibernating in cold, damp caves, places called hibernacula. This fungal growth irritates them, causing them to wake up from hibernation far too often during the winter.
And waking up uses energy.
A lot of energy. Every time they arise, they burn precious fat reserves they need to survive until spring when insects are available again. So they essentially use up their fuel too early and starve or die of dehydration before winter ends.
It's that novel interaction idea again. A new enemy appears, and the native species just aren't equipped to handle it.
Exactly. It's like, as one scientist put it, bringing a gun to a knife fight. The pathogen has an overwhelming advantage because the host hasn't had time to evolve defenses. We saw the same thing happen with chestnut blight, another imported fungus that basically wiped out the American chestnut tree, billions of them. This global mixing dramatically increases the chances of these devastating novel encounters. So we keep coming back to us, Homo sapiens, as the driving force. But why us? What is it about our species that makes us this planetary-scale geological agent, unlike any other creature?
The sources mentioned Svante Pääbo's work on the Neanderthal genome. That was fascinating.
Yeah.
We know now that modern humans outside of Africa carry, what, 1 to 4% Neanderthal DNA?
That's right. So in a way, Neanderthals aren't totally extinct. A little bit of them lives on in us. But Pääbo's work also really highlights the profound behavioral differences.
Yeah, he talked about Neanderthals being sort of local experts. They were incredibly successful within their known territories, but seemed reluctant to cross major barriers, like open water.
Exactly. They were masters of their environment, but they didn't seem to have the same restless drive to expand that Homo sapiens did. Modern humans, by contrast, did things like setting out in boats onto oceans where you couldn't even see land, journeys with huge risks and no guaranteed reward.
Pabo actually wondered if it was some kind of madness, didn't he? Maybe a freak mutation that enabled this human insanity and exploration thing.
He did speculate about that this almost irrational drive to explore, to push boundaries, to dominate new territories. It seems to be a defining characteristic of our species.
And that restlessness, that drive, is ultimately what led us to spread across the entire globe, impacting everything else. There's an irony there, isn't there? We admire the skill in Neanderthal tools like hand axes, but maybe our species' greatest skill was this relentless expansion that ultimately wiped out our closest relatives and countless other species.
That relentless expansion is the engine of the Anthropocene in many ways. It's our ecological signature. We didn't just adapt to environments, we fundamentally altered them on a global scale.
And yet, here's the paradox. We are the species causing the extinction, the only species capable of causing it on this scale. But we're also the only species trying to stop it. We exhibit this incredible capacity for altruism, for trying to fix the mess we've made.
Just a profound contradiction. Look at the efforts to save the Sumatran rhino, Dicerorhinus sumatrensis.
It's an incredibly ancient lineage, right? Going back millions of years.
40 million years, yeah. A living fossil, really. Yeah. And now, fewer than 100 are left in the wild, almost entirely due to poaching and habitat loss caused by humans. Their only hope for survival rests entirely on human intervention.
And that intervention is intense, isn't it? It's not just putting up fences.
It's unbelievably complex and dedicated. Dr. Terry Roth at the Cincinnati Zoo has been a pioneer in their captive breeding, which is incredibly difficult. These are ancient specialized animals.
What kind of things do they have to do?
I mean, it's conservation down to the individual animal. Performing rectal ultrasounds to monitor reproductive cycles, figuring out exactly the right hormone doses, sometimes delivered via progesterone-soaked bread, building special awnings because the rhino's eyes are sensitive to direct sun since they evolved in deep shade. Just mind-boggling levels of effort.
That level of care, that expense for one species, it says a lot about our desire to undo the damage, doesn't it?
Yeah.
Why is it so hard for them to breed, even in captivity?
Well, species with such long evolutionary histories often have very specific, inflexible requirements. Everything has to be just right. Diet, hormones, social cues, environment. They didn't evolve for rapid change or resilience in the face of massive disruption. So when we destroy their habitat and fragment their populations, their natural reproductive systems often just fail. We then have to step in and try to artificially replicate conditions that used to occur naturally.
And we see these heroic, sometimes bizarre-looking efforts for other species, too. California condors.
Oh, yeah. Raising chicks with puppets that look like adult condors to prevent imprinting on humans. Aversion training using mild electric shocks to teach young birds to avoid dangerous power lines. Treating them constantly for lead poisoning from ingesting ammunition fragments in carcasses left by hunters.
Or the whooping cranes following ultralight aircraft.
Exactly. Pilots literally leading the young cranes on their first migration route, flying hundreds of miles from Wisconsin down to Florida, teaching them the way. It's extraordinary dedication.
And even when the battle is lost for a particular species, like the puli, that little Hawaiian honeycreeper, the effort doesn't stop, does it?
No. The commitment often shifts to preservation. The last puli cells are now stored in the frozen zoo at the San Diego Zoo.
The frozen zoo.
Yeah, it's the world's largest collection of cryopreserved cells and tissues from endangered species. It's a last-ditch effort, maybe hope for future cloning technology, but it shows how seriously we take the finality of extinction. Same with the ala, the Hawaiian crow scientists making huge efforts to collect genetic material from the last individuals, even if captive breeding is failing. The grief over extinction drives these incredible, often heart-wrenching efforts. #tag Outrabrand.
So we end up with this profound paradox, don't we? This sixth extinction isn't some random cosmic accident like an asteroid. It's being caused entirely by one species in us.
And the very traits that made us so successful, our ingenuity, our resourcefulness, our relentless drive to expand, are the traits driving the extinction.
That's the core of it. And the sources really emphasize that our own survival is ultimately tied to the health of the biological systems we're currently tearing apart. Ecologists often use the phrase that humanity is busy sawing off the limb on which it perches. We depend on the biodiversity we're eliminating.
Which brings us to a final, really striking thought about the geological timescale. Yeah, the geologist Jan Zalasiewicz makes this point. He argues that even in 100 million years from now, long after all our cities have crumbled and been buried, a future geologist examining the rock layers will be able to see us.
How? what will be left?
Our entire civilization, all the concrete, steel, everything might be compressed into a layer of sediment, maybe not much thicker than a cigarette paper.
That thin.
That thin. But that layer will be utterly unique. It'll contain weird spikes in carbon isotopes from burning fossil fuels, maybe unusual concentrations of metals, plastics that have fossilized, perhaps traces of radioactive elements from nuclear testing. Our brief moment on Earth will leave an indelible, planet-wide signature, a clear marker of catastrophe.
The layer of the Anthropocene.
Exactly.
So the final thought for you, our listener, is this. As you go about your life, remember that you are part of the species currently creating that permanent geological layer. Beyond the carbon signature, beyond the plastic fragments, what unique mark are you, personally, contributing to that layer that will define our age millions of years from now?